All right, happy Monday. Happy last week of classes. I can't believe we're already at our last week here. And it feels like they go faster all the time. So I still need to just sync up the notes real quick. Again, I've been a little slow, so I'll get that going. I believe I caught up on all your grading, hopefully. I think I still have to do, especially for in-person class, I need to do some tallying and midterm correcting. So so far all I did was put in like the points that you earned back. Oh, yeah, you can make a turn-in file. But I haven't like added anything or multiplied anything. So I haven't normalized your grades yet or anything.
What is the juice for the lab?
For the lab, so let's just talk. So due dates, and this would be like in-person turning in stuff by Friday. So this Friday, right, June 6th, I believe it is, 5 p.m. But if you're straggling on anything, you can still email me by next week. So let's just say next Friday would be ideal. What is that? And that's only for like straggling assignments or whatever else. So you could email it. So so that would be June 13th. And that could be up until midnight, or so. I generally check my email like the weekend of grading, but I don't like to be doing things in crunch time. So ideally, trying to turn everything in by the end of this week, including the final, again, ideally speaking. And then, like I said, I will accept, though, all other work next week, but by email. And then, let's also not forget, so we do have our we'll call it our last lab, but it's, at least for the in-person people, a small lab practicum. And it's nothing to stress about. And so that should be relatively simple. And then we'll also have checkout, so that'll be kind of part of your grade. Again, it's kind of just meant to show that you've been alive and participating and, have somewhat of a brain. So again, it's not hard. Check out for freebie points, and we're done with labs. So that is that. And then, we're just finishing up our last chapter, acids and bases. We'll probably still have a quiz, so the quiz will be over, of course, last week. But then we won't have a quiz over this stuff, so that'll just be covered through the final exam. All right, I think that's all logistics-wise. I'll hand back all your papers during the break, and then, again, just kind of double-check your grades, make sure everything looks good as we're in the final stretches here. All right, let's start acids and bases. And I promised a demo, so I'll save it for Wednesday after lab. And so let's see how far we get through our lecture notes. And so acids, so I think people are generally kind of more familiar with acids, obviously. So sour tasting, obviously like lemons are acidic, any other citrus or sour candy. I know I've been super into sour candy recently. And then we've seen this in lab, so they have the ability to dissolve metals. We've seen this with hydrochloric acid and magnesium. And then, of course, they neutralize bases. So that was last week's lab, right? We did a titration between the two of acetic acid and sodium hydroxide. And then we used blue litmus paper to detect the presence of acid. Or, of course, you guys probably had more fun with the universal paper. And then just some common acids and where you might find them. So hydrochloric is pretty common, used in metal cleaning, ore refining and mining, could also be used in food preparation. And then is your stomach acids, of course, right, your digestion continues to take place in your stomach, and part of that is the super acidic environment, which breaks things down. And then sulfuric acid is used in batteries. And then, of course, it can always be used as fertilizers and explosives, as dye production, electroplating. Nitric acid, again, fertilizers, explosives. Acetic acids, of course, vinegar is the common name, so obviously been used a lot in food preservation, both now and historically, of course, is vinegar. So it's acetic acid is, again, just the diluted form. So citric acid, this is just the natural acid form found in lemons and limes. It is interesting, it has 3 protons there, so that means that it's triprotic. So this could also be used to adjust the pH in foods and beverages, used in also candy production. They also use other combinations of other organic acids derived from fruits in like candy. Carbonic acid, so this is what happens when you dissolve CO2 and water. So this kind of goes back to what we talked about last week with solubility and that KHP constant. So okay, now you get all this CO2 dissolved in water, and then it doesn't go directly to there, but then it can form carbonic acid. And so again, that just makes any sort of beverage with carbon dioxide a little bit more acidic. HF, so of course HF always gets the like film sensation for dissolving bodies and such, but it's primarily used for metal cleaning and glass frosting and etching. Of course, it is dangerous. So if you do work with HF, you have to make sure you have the calcium antidote nearby, because if you got it on you, it wouldn't even necessarily burn. That's what's kind of also dangerous about it. But what happens is it goes through and then dissolves your calcium in your bones. And then the problem is that calcium will then re-solidify somewhere in you. So then, of course, depending on where it so happens to re-solidify, right, depends how dangerous HF can be. So obviously it solidifies in your brain, and that can cause an aneurysm. Obviously it's not good. So yeah, if you have work with HF, you always have to keep that nearby, and obviously be very careful with HF. I've never worked with HF. That's kind of on my list of things I don't want to work with. Have no plans on it. And then phosphoric acid, so again, more fertilizer, also used as a biological buffer. And then you do see this in sodas often. So Cokes, or I think, have a little bit of phosphoric acid. And so then what makes an organic acid? So just a quick dipping of our toes into organic chemistry. So an organic acid has this basic structure, and this is called our carboxylic acid group there. And so it's just this proton that's considered acidic, and we can look at the mechanism of how this occurs. So this is, I'm going to draw out just acetic acid, so vinegar as an example here. And so this is our acidic proton, so I'm just going to show its behavior in water, again as a weak acid. But then what we're saying, So kind of getting into this chapter. So water is functioning as a base here. It's going to attack it and take off the hydrogen, and then it puts electrons on our oxygen here, so I'm going to draw that out. So now you have this species plus your protonated water. All right, so and then this species, what makes it extra special is the resonance. So, okay, not only do we have this negative charge here, but we can draw a resonance structure. I probably misspelled resonance. And so all this means is we're going to move the electrons. So we're going to make a double bond here, move these up. And so now we have something like this. So again, these are resonance structures of our carboxylate ion here. And so this is really favorable that this resonance, that this negative charge is stabilized across these two oxygens. And sometimes you see it drawn kind of shorthand like so. And then this negative charge, again, just trying to show how it's across all this area. But that's super favorable, so that's what makes it acidic essentially. But it does have this equilibrium, meaning it's a weak acid, which we'll get into in the course there. So again, identify this carboxylic acid group, and then you know what the acidic proton is. And so like I had mentioned for citric acid, it has 3 of them. And then malic acid, so this is another common flavor organic acid that's used, like I mentioned, in sour candy. So they would use some ratios of citric and malic acid. And again, a potential career, right, as food chemists, how to mix and blend flavors. So looking at bases now, again, just in general. So most people, I would assume, have less familiarity eating bases. So bases tend to be bitter, and so they're often poisonous. Maybe somebody has gotten their mouth washed out with soap. I don't know if people, if parents still do that. But yeah, so soap obviously is basic, otherwise you probably don't want to be eating too many bases. Tonic water though, so that's basics. Maybe you've had that, although I don't know that tonic water is very popular. Yeah, I didn't think people really drank bases. Of course, you may have had maybe like milk of magnesia. That would be another kind of base. So that's often used to treat upset stomachs. And then bases tend to feel slippery. Again, just kind of thinking of your soap, how it feels. Obviously, they neutralize acids, and then you can use the red litmus paper to detect it. And so, of course, common bases are sodium, potassium hydroxide, so those are both used in soap production. So that's always a fun lab to do. No one ever takes Chem 104 and 106 now, and now I don't even know if they run them. But those used to be fun classes because we would do soap production in them. And, you know, again, careers in chemistry, you can get into soap manufacturing, cosmetics, all sorts of things. So both of those are used, like I said, in soap manufacturing. Of course, they have other uses, petroleum and plastic manufacturing, obviously batteries. This would be for both of them. Sodium and potassium hydroxide are used very interchangeably. And then sodium bicarbonate. So this is baking soda. So this is often used a lot as well as a buffer, also a source of CO2, also used as an antacid. So of course you could take, so this is kind of an aside, so Tums, right, is calcium carbonate. So that works to neutralize acid, but of course another source would be the sodium bicarbonate. And so you could mix, right, some baking soda and water and also drink that for an antacid effect. And then sodium carbonate is a water softener or glass cleaner. And then again, all of these can also be used to adjust like pH and like water purification. Yeah, something that was interesting, I don't know if y'all keep up with like the Medford water at all, because they recently like slightly adjusted the pH, because they put out an alert in case like for beer brewers that need to know what pH it is, but they made it like slightly more basic. And I thought it was interesting too that they use, I believe they use sodium hydroxide to lower the pH. Yeah, which, I mean, I thought it was kind of a harsh choice, but you know, it's all like dilution. And then what I also wonder, because obviously we don't have any data, but maybe they didn't want to add too many carbonate ions in the water. So that's the other thing, is like, I don't know what the water is made out of. I mean, we could look at it, obviously, and get into it, but obviously they're the ones that are the professionals and monitoring it, so I'm sure that some of that comes into play, is like, what are the counter ions, right? You don't want to put too many of one ion, and then it might start crashing out of solution. And so why they also adjusted the pH, this was kind of interesting. It was to help with any sort of potential corrosion in the pipes. So if you lower the pH, I mean, we just talked about acids, right, dissolved metals. So they're trying to keep it a little more basic to preserve the pipes. So yeah, pretty cool stuff there with water purification. It's all pretty delicate chemistry, just keeping it all balanced, you know, for the city at least. And then of course ammonia, so that's used, household cleaner of course, also used in fiber production. Once again, explosives, of course, and fertilizer, very important. And so then, this is kind of a definition thing. And so all this is saying, and especially because, I mean, I always like to joke that chemists are kind of lazy. But you'll see this sort of thing where they're like water, and then it splits into H plus and hydroxide. And this is a good shorthand way to show, you know, kind of what goes on and what we're about to get into with water and some of these facts about the pH scale. But all this is trying to say is that we really can't have these little protons existing by themselves in water. And yes, right, again, you're going to see people shorthand this all day, every day. But really, what we want to say is that they react together. So they have it drawn here, so let me, maybe I'll draw it up here. And so the most proper way to think about it is that we have two water molecules staring at each other. And this only occurs 1 out of every like 7, or 1 times 10 to the 7th, which we'll get into. So this doesn't happen all the time, but basically it can happen where one will deprotonate another one, and then we make our hydronium, again, often shorthanded as H plus, and then we have hydroxide. So hydroxide's fine by itself. But again, we will never have just a proton floating around in solution. It'll either be attached to the water or, off doing something else. So let people finish copying that real quick. Oh, the other thing, so I started kind of drawing these reaction mechanisms, and I just want to emphasize action always starts at the electron. So notice, right, I have the electrons attacking, not the hydrogen attacking the electrons. So that would be wrong, and I've seen resources though out there for chemistry that draw it wrong. So all right, so yada yada yada, that's all that's saying. So we don't actually have, again, a proton. It's really hydronium, but they're used very interchangeably. So it says that here, right? Chemists use hydronium interchangeably with H+. All right, so now we'll get into our definitions of our acids and our bases. And so this is kind of the overview, but then we'll look at them and we'll go back and kind of define this Lewis one. And so kind of the most simplest definition, and this works for kind of the common ones we begin to see, is that acids are substances that dissolved in water produce hydronium or H+, and bases produce hydroxide. So of course, right, we have HCl dissociates in water, so making H+, again, right, H+ doesn't actually exist, it's reacted with water here. Or our bases, so again, all our like common group 1 and 2 hydroxides, so sodium hydroxide, or we could go on and on, right, like calcium hydroxide, magnesium, obviously potassium, okay, etc. So those all fit under that definition. So let's look at that. And so again, we're just appreciating how they disassociate. And then of course we can see that they do this simple neutralization reaction, so we can think of it as a double displacement. And then of course we always form water in this case, and then whatever salt. And so here's an example. So again, acid plus base, so our simple Arrhenius definition plus our Arrhenius definition base, again swapping their partners here. So now H goes with OH to again make water, and then our salt. And so the problem with this definition is that it's too narrow. And so if you can, even just think of lab, well, right, you've worked with ammonia, and well, this doesn't explain why ammonia is a base, or, again, we often see it in lab as ammonium hydroxide. Well, why is that, right? So we don't get that explanation. It doesn't tell us how sodium carbonate or sodium oxide also form basic solutions, even though, right, there's no OH attached to them. And it doesn't explain why CO2 makes acidic solutions, even though it doesn't contain H+ ions. And so it also doesn't explain kind of other acid-base reactions. And so then this brings us to our Bronsted-Lowry definition, which again is not all-encompassing, but this one looks at our proton transfers. So this is sufficient again for our class. And so now any reaction that transfers a proton from one to the other is considered an acid-base reaction. And so now let's look at some examples here. So let's skip down to ammonia. And so we kind of have this definition here. And let's look at ammonia. And so I'm just drawing out ammonia so we can see, right, the lone pair's structure. And then we'll look at its behavior just in water. Sorry, I'm just redrawing water here. And so then we kind of define roles for everybody. And so in this case, our ammonia is acting as a base. And I really like the Lewis definition better because, well, A, it's all encompassing, but it's kind of easy to see in a lot of ways as well, because again, action starts from the electrons here, and so we can tell that this nitrogen basically wants to react. So then, again, this is acting as our base. And so our base is just defined as something that wants a proton, and so that is what happens in this case. So again, right, it deprotonates here. So now we form our ammonium. So now the ammonium cation, and then of course hydroxide. And then we can see how our definition shifted. Oh, so I should define, so water we're going to get to is amphoteric, which means it can act as an acid or a base. So in this case, right, it donated a proton. So my water is acting as an acid. All right, so it lost a proton. So that means that my acid, so my water, now becomes my conjugate base. And then just compare those relationships, right? So they're different by a proton. So acid to conjugate base, again, they just lost one proton. Okay. And then our base now becomes our conjugate acid, since it has, again, an extra proton, right, compared to your original base there. So again, just watch out for that. So it should be just kind of one proton at a time action. Give people a second to finish copying. And so again, just by definition, our Bronsted-Lowry acids are H+ donors, and any substance that has basically an acidic proton, so I'm just going to add that term. So again, acidic proton, just like we saw in the carboxylic acid, basically it has to be a proton that's favorable to leave, and you'll get into this definition more and more, again, if you go into CHEM and kind of what that means. And it does kind of hint at where this is going, but again, right, we're only 100 level chemistry right now. And so it makes the point that there's often one hydrogen in the molecule that is easier to transfer than others because of the structure. So again, right, that's referring to carboxylic acid, potentially, or any other organic acid. So there's other protons around here, but they're not acidic, so it's just the one. And so again, right, our Arrhenius definition still applies. So HCl still acting as an acid, donating a proton, and water here acting as a base, since it is accepting it. and then our base becomes our conjugate acid. Our acid becomes our conjugate base here. So again, just definitions. And then a base has to be an H+ ion acceptor, again, just like we saw with ammonium, and those electrons grabbing that H+ ion. And so again, we went through this, but here it is. So again, base-acid relationship, acid to base. So plus a proton minus a proton. So just kind of keep track of that. And so again, I mean, this is not necessarily exclusive to this, because again, you could use a Lewis acid-base definition, but it's helpful just to, again, see where this proton is transferring to and start thinking about that electron action. And so something you want to be able to do is identify what's called these conjugate acid-base pairs. And so like we saw earlier, our base becomes our acid, and our acid becomes our base. And so each of these is called a conjugate pair. And like I was trying to emphasize, the difference is a proton between them. So you can always tell if something is a pair if they're different by a proton. And so what I also will warn you about is don't get tricked by things like this. So is this a conjugate acid-base pair? Oops. So what is this, an acid-base pair, or what's wrong with it? So what's, I see you shaking your head, what's wrong with it?
H2O and OH, wouldn't that be an Arrhenius pair?
Yeah, so you identified what it should be. So H2O and hydronium is the correct pair. And then right hydroxide and H2O is the other correct pair. But what's wrong with this one? You've identified that it's wrong, but what makes it wrong? And kind of going back to this concept too. So what did I say had to be the difference? How many hydrogens?
Three.
So there should be just one difference, right, between an acid-base pair. And then here it's 2 hydrogen difference. So we have OH, right, so we have 1 hydrogen, then we jump to 3. So 2 hydrogen difference, so not a proper pair. But again, right, these were proper, so we have 1 hydrogen, then we went to 2. So okay, that's just 1 hydrogen difference. So that's good. Same thing with this one. So again, right, 2 hydrogens to 3 hydrogens. So 1 hydrogen difference again. So that's what distinguishes, again, what's a proper acid-base pair versus something that, you know, you could see on an exam for a trick question. And now this also kind of answers why ammonium hydroxide and ammonia are used interchangeably in lab, since again they're in this solution, and so you have this equilibrium going back and forth. So of course they've drawn it in this direction, but we could also draw it in the other direction. Or draw our, because we can also draw the opposite reaction that's going on here. So if we have now ammonium in solution, so now this would be our acid, right? So it was our conjugate acid. Now it's our acid. So we can react it in the presence of water. So it's going to give up a proton. Water will act as our base. And so now we reform ammonia formally. So our conjugate base, and then make hydronium, or H+. And so this is our conjugate acid now. And so we can, again, just kind of appreciate this equilibrium, this back and forth behavior. And then, yeah, we'll get into this as we, again, kind of progress through this chapter. But this is also why we're going to find out that ammonium is considered an acidic salt, since it can react with a base to form acid here. But like I said, that's kind of coming at the end of the course, but just if you can kind of start to see that, and by end of the course I mean in 2 days. But all right, let's see if we can practice here. So again, who's acting as the acid, who's acting as a base, and then where's our conjugate acid and conjugate base species. We'll zoom in on that here. So I just sketched out the first one. And so, right, you can kind of look at our reactants, look at our products, try to piece together what happened. And I'm kind of looking at this, right, looks like our sulfuric acid gave up a proton and our water accepted it. You can even draw out a little mechanism. So then H2SO4, so is this our acid or base?
Acid.
So acids, that means water is acting as base. Excellent. And then HSO4 minus becomes our
Conjugate base.
yeah. Let's say it louder in the back too. You had it. And then H3O plus is
Conjugate acid.
yeah, conjugate acid. Excellent. And then let's look at the second one. So then what happens in this one? Kind of what happens to the water? Who's our acid? Who's our base? So what's water acting as here? What happened?
Acts as an acid.
So it acts as an acid here. And so we can tell that since it lost a proton, right? So we have this hydrogen carbonate over here. So in one of the many steps to our carbonic acid equilibrium, one of three really. And so then, okay, we can see that this was our base, and then H2CO3 becomes our what then? Conjugate acid. Good, so carbonic acid, and then of course we form hydroxide, which is our conjugate base. Excellent. Questions on that? All right, maybe we should, yeah, we'll take our break now. So we'll take a 10-minute break. I'll try to hand back all your papers and stuff, and then we'll keep going through this. So we'll look at the strong acid, weak acid a little more in depth. All right, let's get papers. I was going to email you, but
I emailed you this morning.
yeah.
So, okay.
I didn't email you back, did I?
No.
Yeah.
No.
Okay. Yeah.
You're not crazy, you know.
Yeah, corrections are in the grade book, but not the total grade yet.
I saw that.
Okay, yeah. I haven't. And then you can still do corrections since it took me so long.
Did we have homework this week?
Oh, did I forget to put it out?
Yeah. I was wondering that.
I was gonna say something.
Oh, it's here under this pile. Okay, sorry. So yeah, there's homework and the lab. Oh, we don't have that lab. I'm sorry. We did. I forgot we're doing the lab crack again this week.
We did it last week, right?
Yeah. Oh my gosh. Blame pregnant brain. I was just trying to hand y'all something. You might have put it down on it. Yeah, most of the labs were pretty good anyways.
Did you ever get my lab one? So I don't have a grade for it in there.
That's weird. It should have been returned to you as well by now. Do you have it?
I might. I'll have to check for it at home. I'll bring it in on Wednesday.
Yeah, a really good picture.
Worst comes to worst, I'll review it.
Yeah. It should be somewhere. I did have some like older papers chilling on my desk. But I think these are people. Right there in this pile. Is your laptop gonna make it?
Huh?
Is your laptop gonna make it?
Oh yeah, it was full charge when I left.
Okay, good. I don't see other papers from you. Shouldn't have been citing famous last words. Yeah, let me at least glance around my office real quick and make sure there's no hidden stacks of anything. find anything hiding in there. So just check your papers.
Probably somewhere in my lavender paper we're trying to get to organize through.
So I'm hoping. All right, so let's continue. So like I said, I'll bring the demo in on Wednesday, so we'll have kind of more fun with that. And now so we can compare our definitions of what a strong acid is versus a weak acid. And so it has nothing to do with like how dangerous it is or how much it can burn you. It's just, again, does it completely ionize or not? And so we have, and I should have printed this out. I thought about it and then I'll bring it on Wednesday. So up at the top, we have by definition our strong acids. And so they're telling you that they're strong acids, and since it says undergo complete acid ionization in water. So that's perchloric, sulfuric, and notice sulfuric, it's going to be the first deprotonation, so losing one hydrogen. And then hydroiodic, hydrobromic, hydrochloric acid are all strong. And then nitric. Notice who's not in there, HF. So HF is a weak acid, so that's kind of, I mean, you may find that surprising, because again, right, TV always tells you HF is so dangerous, which again it is, but that has nothing to do with its dissociation, which is all that we're looking at here. And actually, on the safety note of HF, so this is where fluoride could become a potential issue as well in large concentrations, so especially if you're a chemist doing a reaction. So now let's look at HF and its equilibrium. So again, let's just look at it in the forward direction first. So HF in the presence of water. So of course it's going to form our hydronium here and fluoride. And might as well label everything. So right, acid, water is acting as a base then, since it took off the hydrogen, and then now we form fluoride. So of course our conjugate base, and then obviously hydronium, conjugate acid. And then, so the danger of our fluoride here is, of course, so now let's do the other direction. So fluoride then can react with water. So now this is our base. Water's acting as our acid, so giving up a proton. So now we can reform HF, and then we also are left with hydroxide. And so this, we'll later learn, also makes fluoride, again, a basic salt. But this could be potentially dangerous, again, if you're trying to think about neutralizing waste. How do you take care of your reaction waste? And so if there's a possibility of generating fluoride, then you should potentially neutralize it, so add some more baking soda or something, or another appropriate base, so you don't have any HF floating around potentially. And so then going back to this chart here in concepts, so then, right, a strong base, same thing, strong electrolyte, so I would just put in here, this tends to be our group 1 and 2 like we've seen. Again, complete dissociation. And then our weak bases, we'll only look at a few classes, but really it's going to be what are called these ammonia or amines here. So those are the main bases, weak bases at least. And so then this is just to make some comments about general trends. And so let's look at this. So the stronger an acid is at donating a proton, the weaker the base is at accepting a proton. And so what this is trying to hint at is kind of the strong acid, weak base concept. So again, let's put some context to it. So if we look at HCl, and so strong acid, so the better it is at donating this proton, then the weaker the conjugate base is. And actually in this case, right, HCl, strong acid, so that means that its conjugate base here, chlorine, is such a bad base that it can't even accept a proton. So again, this goes back to the definition of why it is a strong electrolyte. But we're saying, okay, this reaction to reform HCl and make hydroxide does not occur. So I need to put a big X through that. And so that's, again, kind of what it's hinting at. Okay, so HCl, strong acid, that means conjugate base cannot accept our proton. And then again, thinking about something in equilibrium, like our acetic acid. So that one has equilibrium, so it can deprotonate to make acetate. And then this acetate, right, can go on and reform acetic acid. Since again, right, it can, the conjugate base can accept a proton. So that's all that is trying to say. And then other general trends, the more oxygens, the stronger the oxy acid. So this is comparing like sulfuric and sulfurous acid and nitric and nitrous acid. And then this is helpful when we go back and try to classify salts. So a cation is a stronger acid. And so now this goes into cations are usually going to be acidic or neutral. So that's all you'll have to decide. And we can already think about that with ammonium, sorry. And then neutral molecules are stronger acids than anions. So, right, anions tend to be bases, which that kind of makes sense. And we can kind of pause here to go back to our other definition. So I kind of neglected the Lewis one at the end, because like I said, we don't necessarily want to get too deep into it. But I really do like the Lewis definition. So it is, like it mentions here, the most expansive. And we see that acids are something that accept electrons. But the big one is, right, bases donate. So we're always kind of seeing that base donate. So that's why, okay, if we're talking about an anion, right, it has to have electrons to donate. And so this kind of plays back to this definition here. And so again, just kind of general trends. You can compare hydronium, water, and hydroxide. Obviously, hydroxide's the base. Makes sense as it's negative. And then ammonium, ammonia, and then NH2 here. Again, this is going to be your acidic. Obviously, this is basic, and then this would be even more so. And again, you can imagine that since it has a negative charge, so it really wants a proton. So I'll print this out for reference, since again, this is kind of a handy chart then. So we keep kind of going through what it's telling us. So right across is going to be, again, its conjugate base. And we see that these say do not undergo base ionization in water, meaning they can't reform the acid. So that kind of, again, helps identify. And so that means then when we get to the salts, these are all going to be neutral. Again, we'll go back to this concept. I'm just trying to lay it out. And then we look at hydronium and water. So again, conjugate acid, conjugate base pair, hydrogen sulfate with sulfate. So this is helpful to just kind of also identify acid-base pairs. And then now we get to our end here. And so this also helps us. So we have increasing basic strength on our bottom, increasing acid up top. Obviously they're opposite, kind of what we said. And then we can at least just appreciate this. I don't think we get too much into it. Again, we'll save it for 200 level. So all we're saying, well, let's look at what our Ka is. All right, so we should have defined this a little earlier. Let me rewrite it up here, actually. So anytime we look at our acid disassociating, we have this, what's called Ka constant. So I'll do it for HF as a representative. And so we're looking at this reaction. So water doesn't count in our expression since it's our solvent. But then we're looking at, so this is our coordinated HA, right? So where they're still together, our acid. So in this case, HF. And then we're going to figure out how much separated. So how much A minus, or fluoride in this case, right? Acetate, if we're looking at acetic acid, is made versus how much hydronium concentration. So this is always hydronium. And so then you're left with our equilibrium expression. And so I don't know if you guys remember, it is on your exam, the equilibrium. I don't even know if I remember what chapter that was. Was it 7 or 6? Well, anyways, we can look at the equilibrium section later if we need to. But basically, so if you dig out your notes from before, right, we had our equilibrium set up. So, right, we had this AA, BB, gives you CC. Does this kind of ring a bell to some people? And so we had written some basic equilibrium expression of products over reactants, which ended up, I'll write it out right, you have C to the C times D to the D, A to the A, times B to the B. Okay, so we have all that. So I'll let people rewrite and refresh themselves. And so all we're trying to do is write our equilibrium expression then based off of this for our reaction here, generalized, right, for any acid. So that's what our Ka is. So Ka is then, right, specifically equilibrium of acid here. And so it's, again, generally kind of given in this format. So again, products over reactants, so how much disassociated over how much stayed associated. And so all that to say is now we want to at least understand these trends. And so we had set up here as strong acid then is going to have a Ka much, much greater than 1. And again, this makes sense. So if we're saying, okay, well, HCl, again, it fully disassociated. So products over reactants, we're basically going to have, you know, a whole ton over almost nothing. And so it's going to have an extremely large Ka. I wish they had given us some as an example, but I would assume like 10 to the 36 or something ridiculous. We'd have to look up the quantification. And so again, that's what defines our strong acid. So just other ways to define it as fully disassociating. And there are strong acids again. And so then if you have a weak acid, all that means is that your ratio is less than 1 of, again, just kind of generalized products over reactants. So saying, well, I have some disassociated and some still associated. And I think this will, again, you'll kind of have a better appreciation of it when I actually light up the light bulb and you see how dim the acetic acid is. But like I said, I'm saving the demo for Wednesday. And so I'll bring in acetic acid. We'll see how much dimmer the light bulb is. And then, right, like I said, just get a physical sense of that Ka. Blah, blah, blah. And so other things, so this does give us the strength. So of course, right, the farther the equilibrium position lies towards the products, the stronger the acid or the base. So that's reflected in these constants. So again, we're not trying to get, what is up with this? I want to pick my highlighter. There we go. Okay, I don't know why it's not changing. But it's reflected in this little order of magnitude here. So 10 to the negative 2, so that's fairly strong, right, compared to 10 to the negative 10. So, right, smaller number, so less products there. So then that tells us that this chlorous acid is stronger than hydrogen cyanide here. And so again, here's them laying out the work with the equilibrium constant. So that's, again, how we derive this Ka expression, products over reactants. Like we saw, we don't include water since it's our solvent. So concentration, right, is not really changing. And then this table is here just kind of more for our fun and appreciation, and then also helps at least with a few acids and how that equilibrium process looks. You can, again, appreciate that. Something else to note, so right as their pKa's go up, that means they are a weaker acid. And we might as well go over the relationship. So the pKa is equal to the negative log of the Ka expression. So that's how you go from one to the other. You can, of course, also get the Ka from taking 10 to the negative of the pKa. So you can go back and forth. Again, I don't think you'll need to do that too much in this class. That's kind of a preview for 200 level, or how you would approach kind of these equilibrium problems later, but we're not going to attempt to solve them in this class. So again, just kind of appreciating the strength. So to note, again, the stronger acids are on top. So chlorous, nitrous, HF, and then we have formic, benzoic acid, acetic acid. And so I would just kind of look at the structures for these. So there's our carboxylic acid group, so those are organic acids. And then phenol here is kind of interesting, just because you may not expect it to be acidic, but it is weakly acidic since it has this aromatic ring. So again, it can stabilize a negative charge. So that's pretty cool. But again, just kind of appreciating it. And so now we want to get into our pH scale. And so this goes into what we had kind of talked about earlier. And so water is amphoteric. So like we've seen with this term, that's just any substance that can act as an acid or a base. So I'll put in, right, like hydrogen carbonate would be another example of something that's amphoteric, right, since it can lose a proton or gain a proton. And so water does the same thing. And so at some point, they were trying to like figure out basically how many ions exist in water. And so that's where this came from. And so they determined, and like we mentioned, right, we really want to think about it like this, of two waters reacting, right, as opposed to the water just disassociating, since again, we can't really have just a naked proton, so it's really hydronium, but again, just shown both ways interchangeably. And so what they found was about 2 out of every 1 billion water molecules form ions through this process. And so now this is teasing to how we got to our pH scale. And so they found, well, all solutions contain both hydronium and hydroxide. And then it was also measured that these concentrations are equal in water, at least at 25 degrees Celsius, again, when you just have neutral water there. So that's what they found. So again, this is important, right, that they found the concentration to be 1 × 10⁻⁷ of each of these. And so again, this is kind of teasing where pH 7 is neutral comes from, but we're getting there. And so now we have also a bunch of relationships that help us solve pH. So we have what's called our ion product of water, Kw. And so all that's saying is that these two numbers together always equal 1 × 10⁻14. So you can set this up so hydronium concentration times hydroxide concentration equals Kw. And again, this is at 25 degrees Celsius, so for our purposes, right, this will always be true. So obviously, just understand deviations can occur. And so then, as obviously one increases, then the other must decrease to stay proportional. So they're inversely proportional there. And so again, this is just by definition, so all solutions contain some amount of hydronium and hydroxide. Like we saw, well, that was how they established what a neutral solution was again, they measured these concentrations and found them to be equal. And so acidic solution is defined as anything with greater hydronium than hydroxide concentrations. So of course it's going to be greater than 1 times 10 to the negative 7. And then basic solutions will have more hydroxide than hydronium. And so see if you can figure out who's acidic, basic, or neutral off of this, and then we'll reveal the easier way, we'll say, to calculate it. So what do we think about A? Acidic, basic, neutral? Ten to the negative fifth. So how does that compare to 10 to the negative 7? What do we think?
That would make it basic. So,
Oh,
right.
it's negative 5, right? So it's higher.
Yeah, more acidic.
Yeah, so then it'd be acidic. And then what about, so 1.5 times 10 to the negative 9.
Basic.
So basic. So now that's easier to tell off of that one. And then 1 times 10 to the negative 7. So neutral, so right at 7. And then I do feel like I kind of cheated y'all. No, I'm joking. Because, right, this is the harder way to measure pHs or compare them, looking at those exponents. Good practice, though, for the brain. But then, so now we'll reveal the pH formula. So pH is the negative log of our H+, plus concentration. Oh, sorry, I didn't have my calculator fired up. I need to pin it to my start menu here. And so now we can go back and look at these. And okay, so negative log. And then just make sure that you're practicing on your calculator, because sometimes you can have a calculator that's like in a different base or something strange. But it should be in base 10. And so if we plug in our negative log of our H plus concentration, then we get about 4.12 for the first one. And so that's a lot easier to see that that's acidic. Something that can also kind of help you is you can like roughly guess the pH by the order of magnitude, because I was going to guess about 5 for this one, so that kind of works. And then B, so negative log of 1.5 times 10 to the negative 9. And so roughly 8.8, so I was expecting about 9. So that's, again, easier to see who's acidic, basic, or neutral. And again, do appreciate that we are on a logarithmic scale. So, right, everything scales by a factor of 10 when going up with this pH scale. So, again, just keep it in mind when you're talking about order of magnitude or thinking about the difference there. And then we just have a few examples for context. So like we mentioned, the pH in our stomach acid is pretty low, so about 1 to 3 for the pH to aid in digestion. Limes and lemons are also pretty low. That's where, I don't know if your dentist has ever warned you, right, like not to suck on too many lemons either, or like especially don't eat a lime and then go brush your teeth, right, because that'll really add to the wear and tear, since they say, right, the acid kind of wears at your enamels, and then you don't want to scrape it away with a toothbrush. And then, of course, soft drinks can also be pretty acidic, along with fruits, wines, and then we start to finally go up in pH a little. So beer, right, still a little bit on the acidic side. Rainwater could be somewhat acidic. Again, it kind of really varies where you sample. Human blood, if anyone's taken any biology, I'm sure you know that has to be, kept at a tight pH, right? So it has their 7.3 to 7.4, since all your body chemistry is pretty sensitive. So keep that pH in the correct range. Egg whites, so those are slightly basic. There's milk of magnesia, again for stomach aches, and ammonia for cleaner, and then of course NaOH is super basic.
It's 14 the highest you can go.
You can, I think, go higher in theory. I don't have like examples off the top of my head, but it kind of like depends how you measure it. There's also like super acids too that like technically I think can have negative pHs, but yeah, those, it just goes back to like how you define an acid and like different things, but yeah, because they use carburenes, I believe, as the basis of some of these super acids, but I'd have to pull up those papers. And then other good expression is this. So to go back and forth, so let's say you need the hydronium concentration, then you can take 10 to the power of the negative pH, and that gives you back the concentration. So I really like the pH chapter for that reason. It's kind of circular, so you can always kind of check and recheck yourself, which is nice. And so again, like we're seeing, this is just the general scale of how to measure it. And again, pH 7 being neutral. And this is where we get the scale goes from 0 to 14. Again, with obviously some exceptions, but it's the main scale. All right, so see if you can calculate these two. And this one's a little tricky, but think back to what else you were given. So I'll let you try to puzzle those. So what did we get for A for the pH? That was at least hopefully straightforward.
Roughly 3.7.
So 3.7. Do you have another sig fig by any chance?
4.472.
So 4. And so sig figs for log, so if you plug in 2, then you get out 3 for your pH. But I won't be too stickler with those sig figs on these since it gets a little strange, but try to remember to add another sig fig. All right, so that looks good. And then did we figure out how to approach this one? What was one relationship we could use? What else were we given? What do we remember?
The KA equals 10 minus PKA.
So pKa, but that doesn't help us here. What other relationships were we given? Was there something of hydroxide and hydronium? So what about this relationship, our KW here? So this will also tease at our next formula, but we'll present it in what I think is the harder way. So that's, again, one way to approach this is we can use our relationship given. So hydronium times hydroxide concentration had to equal 1 times 10 to the negative 14. So then we can solve for hydronium here to get our pH. So 1.3 times 10 to the negative 2. So now, oops. So I'm going to plug that into my calculator. So just divide so we can solve. Oops, sorry, got that wrong. 1.3. And then we should get this answer. So 7.69 times 10 to the negative 13. And then we can plug in for the negative log of that to get our pH. So then our pH would be 12.11 there. Although we are about to learn another formula. So I'll let people copy that down. Questions on this before I move too fast? All right, so then we have POH. And so this is just another way of, again, saying how acidic or basic something is. And it's basically the opposite of our pH scale. And so again, we have some more formulas, so we can find our POH by taking the negative log of our hydroxide concentration. Or again, pretty similarly, we can go from POH to hydroxide concentration. And so I like this chart so we can see, okay, up top is our regular pH scale, so it goes from 0 to 14. Up bottom is our POH, so exact opposite, right, 14 to 0. And so maybe you saw this coming, but this is super useful then. So instead of using our KW relationship, we can skip to our pH plus POH equals 14. And again, this is assuming 25 degrees Celsius, where our KW is 1 times 10 to the negative 14. And so this is just a quick derivation of why that is. So you can remember kind of your log rules. So this just starts off with our KW formula here. And then we take the negative log of both sides. So negative log of this is just 14. Negative log of each of these is just pH and POH by definition. And so that's what I kind of mean that this pH chapter is pretty circular, right? Because we have this relationship, or we could solve for POH, right? So we can now go back to B and say, well, maybe I'll just get my POH instead, right? So then I can get my negative log of 1.3 times 10 to the negative 2. So that gives me my POH. And so now let me write that down as an aside here. So, okay, now we have all our tools in our arsenal. So calculate our POH. So 1.88 or 1.89 roughly with rounding. And then 14 minus this. And now we're back at 12.11 again. So however way you want to get to it, right, you'll get the same answer, which is kind of nice. You can check, double check yourself. So I like this chapter for that reason. All right, so then buffer solutions. This is, again, just definition, so solutions that resist changes in pH when an acid or base is added. And so then we kind of saw this in lab, but then we'll kind of look at it because it's a mixture of both kind of neutralizing this acid and base, and then of course, right, you have a little bit of Le Chatelier's principle working. And so buffer solutions are made up either of our weak acid and our conjugate base, or if you had a weak base, then it's conjugate acid. So a common buffer solution would be like acetic acid, and then its conjugate base would be acetate, so like sodium acetate would be an appropriate purchasable chemical, I like to say, right? Because you can always draw up whatever all day, but then, you know, it's always about what can you actually purchase and buy to get there. So that would be a good combination. So then a weak base conjugate acid, just to give an example, would be ammonia, and then, right, like ammonium chloride. So like I said, we're not going to see a lot of variety in our bases, so mainly these amines. And so it mentions, of course, that this is how blood functions. So again, it's a pretty tight buffer solution, so it's a carbonic acid based buffer and hydrogen carbonate. And so again, just telling us how to make it. So there's our acetic acid sodium acetate combination. So it just has to be the acid and the conjugate base. And then, so this is pretty wordy, right? But then let's just kind of dissect what it's trying to tell us here. And so, of course, we also can't overwhelm our buffer, is what I always say. And so obviously, right, you could take a buffer and just overwhelm it with a large amount of strong base. But let's just look at a small amount. And so then kind of how to approach these problems is, well, first, what's the reaction that happens? So that's all that's shown here is, again, right, you have your buffer component. And so your buffer is either going to have your acid or your base. So acid base. So obviously, if you're adding a strong base, it's going to react with your acid component. So this is just our neutralization. So forming water and then sodium acetate. And then this could cause, right, a slight increase in our pH. But again, we can think about Le Chatelier's principle. So what helps these buffers is, of course, right, this acetate can reform our acid and kind of go back and forth in equilibrium. And so as long as the amount of sodium hydroxide is less than our acetic acid, right, our pH change is small. And then, of course, okay, looking at the alternate scenario, so now if we add a strong acid, now we want to react it with the base component. So now it's reacting with sodium acetate. Again, just doing our double displacement. And so this is cool because we'll reform our acid here. So this is just HA again, right? We can call this A minus. So we can kind of use the same terminology. And then we make our salt here. And then we expect it to change a little bit, so slightly decrease or not at all. Again, as long as we have less than the amount of sodium acetate. And so like I was hinting at, right, this is Le Chatelier's principle. Again, is basically we do our reaction and then the system can come back to equilibrium. And so that's all that. is talking about. So this will be useful for our class. I would have to glance back at your exam to see if you need it. But this is the quick and easy way to handle these buffer solutions and how to determine the pH. And so the pH is just equal to the pKa. And so, right, this is something that you have to look up. It was, again, how acidic something is. So this is one reference point for, right, the pKa. Probably if we'll work with anything, it's going to be acetic acid with 4.74 for the pKa. And then this log of base over acid. And so first of all, you might see another form of this expression on your homework or, on the internet, whatever. And so this is log of base over acid, right? So A minus over HA. But the alternate form is pH equals pKa minus the log, and that's because they've done acid over base. So that's where you get differences in the formula. So just watch that. I like this one. I don't know why. Probably just that's how I learned it. So I always just think the plus sign and base over acid. And so this will be how we calculate the pH of a buffer solution, like on homework. And again, we won't worry about this exosmol approximation. So for our purposes, this will always hold true. And this is kind of more for the 200 level class. So for our purposes, right, we can just determine, like for example, if we were making a buffer, right, you can figure out how many moles of base, how many moles of acid, and these should technically be molar concentrations. But usually you just look at moles because the volume should cancel out, right? They should have the same volume. So it's starting to get a little more nuanced, but like I said, we want to keep it basic for our purposes here. So then we would just want our molar concentrations, base over acid, and again, let's just say you were doing a reaction like so. So going back to one of these scenarios, right? I don't think we'll do that in here, but I'm just trying to prepare you for how to think about these. Is, right, you have your amount of base, you have your amount of acid, you do the reaction, you figure out, right, how much base is left, how much acid was created, and then you can plug that into your Henderson-Hasselbalch. But like I said, I don't even think we'll get that advanced in here. I'd have to look at your homework when I printed. All right, I think we're running out of time for today, but that's where we'll pick up on Wednesday, so we'll probably do some examples of this, and then we'll continue with the salts, so kind of going back to these concepts of acidic, basic, neutral, and equilibrium, and like I said, we'll do our demo then. All right, I'll try to get these notes online ASAP, and then Wednesday for lab practicum. I think that's it. Let me know if you need help with the final. Ideally, everything turned in paper by Friday. Otherwise, like I said, email deadlines for next week, so just keep an eye out. And again, double check your grades. Everything should have been handed back. I'm just glancing around for, yeah, so everyone should have their papers back. So let me know if stuff is wrong in Blackboard or needs fixing. And I'll continue to work on your Blackboard grades. All right, I'll hang around on stream for another minute or so just in case there are questions. Otherwise, I'll see y'all for lab on Wednesday. And yeah, anything to turn in.